but it is the same session, and I'm going to speak about how can we outperform Spark with Python. So first of all, who am I? Oliver didn't know this, but I'm actually using Henrik as my name. The reason is that all males in my family are called Christian for some odd reason. Apparently the last name wasn't enough for a common name. So we also share the same first name. So I'm using Henrik. I'm a principal architect at a company called 2Day. And then I teaches AI and machine learning it's a program called Ready School, which is immigrant women and refugees who can't get job in Denmark, but is still very highly educated. So I'm teaching professors and masters and so forth. So I'm part of a few conferences where I volunteer in the different program committees. Then I have a few Microsoft certificates, and I've been building everything from computer games to data warehouses. I actually started programming when I was like 8 or 9 years old, so I've tried a lot of stuff. So I also write a lot. I have my blog where I'm also covering some of the things we're going to speak about today. And on my blog, I'm also trying out, things which is not meant to be done in Fabric. And I know don't expect to learn anything useful from this post, but I learned a lot of stuff about Fabric when I did it. So yes, on a last note, I can say I'm also an aspiring author. I can't reveal what I'm writing right now, but hopefully it's going to be in early release next month. So let's get started. We're going to speak a little bit about the concepts and in terms of Apache Spark and Python. And the reason for that is that we're going to look into how can it be that Python can be faster than Apache Spark. Then we are going to see some scenarios where it's better perhaps to use Python there, to use Spark. And we're going to look into, we're going to speak about the compute, and also we're going to speak a lot about Apache Arrow and how we behave when we are using Python. So if we just get started with the concepts and principles. When I first did the speak, I was talking to a person, and he asked me like, okay, how can you outperform Spark with Python? Because isn't Spark using Python? And what I understood for that is it, what if I said how to outperform SQL Server with SQL? I can understand if that the reasoning people are doing it when I'm saying outperforming Spark with Python. So I think, let's dive a bit deeper into that. So we can't really have a Fabric speak without showing a picture like this where we have some ground thing and a lot of service on that. So Spark come in a package with different modules, and the Apache Spark or Spark Core is the engine, and then we have the Spark SQL module, which that's the module all of us are using more or less. And what can I say? The rest is not important for that for this session. So if there's any questions about that, you can just write to me. Okay, Spark is a cluster, and the head of Spark is called the driver. And the driver node is controlling a lot of worker nodes. So when we do a SQL or PySpark, it's actually not being processed on the worker nodes. What these two languages does is they are building on a plan. And we can also use R to build on that plan, or some other languages. At some point when we do a write or display or so forth, this plan gets executed. it goes through the Catalyst optimizer, and out comes a new plan, and that new plan is going to be chopped into tasks and sent out to the executioners, and they are processing the plan. So after the unresolved plan, as it's called, when we do an execution, what language you used to write your statements are no longer important. It will all end up in Java bytecode. So all this and the administration of the executioners, there's an overhead in this, and it's actually quite big. But we're going to look into that as well. On the other hand, we have the Python. And in Python, we usually have a server. And in Fabric, that's the same case. And in Fabric, we are starting with 2 CPUs. We can actually do a lot with these CPUs. But of course, if our data sets are big or we need some more compute, we can get up to 80 CPUs. And for each CPU, we are getting 8 GB of memory. So we can actually get over half a terabyte of memory for the task we are doing. And then it's not as nice as doing Spark SQL. So our SQL has to be in strings, but it's manageable. And we're using Python, as we're using Python when we're doing PySpark and work in the notebooks. But there's also something which is a little bit secret, because we're always speaking about, okay, we're using Python to do something. We are using pandas, or we are using Arrow, or we're using Polars and so forth. But the truth are, we're actually not using Python. We're using native compiled libraries, and we're operating these with Python through Python bindings. So actually, many of the data frames libraries we are going to see here is actually native compiled libraries and engines, and they work on a server. And that's where Python can get its blazing fast speeds from. Then we're also going to touch about data frames, because there are data frames and then there's data frames. And all libraries has the concept of data frames, but they're actually not that interchangeable, and yet they are. But let's start. So a data frame is much like an Excel sheet, if I have to draw parallel. And that data frame is usually living in the memory. So that's an in-memory data frame. And when we work on an in-memory data frame, it's actually very fast, because we are working directly in the memory. And to compare it to Power BI, for example, it will be the same as an imported data set. We also know, okay, when the data is imported, it's very fast to operate on. On the other hand, we have lazy loaded data frames, the one we know from PySpark. And the thing is, in-memory data frame, we have one server, so we have a unified memory, so it's just loading in data. When we have a cluster, we have the memory spread out on the cluster, so it's not unified. So we can't just load data into the memory and process it. So we have to do a recipe where we are telling, okay, you need to read the data, we need to process the data, we need to write the data again. And that recipe will get sent out to the cluster, and then the cluster operates on the data according to the recipe. So that's the main difference between in-memory data frames like pandas or polars or arrows, arrow, and then Spark data frames. So, and of course, if there's any question, just ask them. Then we have, I'm going to start a little bit easy here. So we have the thing about procedural data processing. That's the best term I could find about it. And what that means is stepwise data processing. I'm going to show you what it is. So where Python really can shine over Spark is when we are in the area of the bronze, and perhaps also in the ingest. reading. And the reason for that is that often it's files we are copying, or it's JSON we are ingesting, or CSV, or so forth. And it's like normally when we ingest things, it's usually in smaller batches compared to when we are moving things from silver to gold, or gold and out. So we're going to focus a lot in this chapter, a lot in this section, around the bronze. And as I said before, usually we have a source, we have a bronze, and the notebook utils, that's Swiss Army knife in Fabric. It has the copy command, and we can actually get very far with that. So let me show you something here. So this is, Fabric, a Fabric notebook, where we can switch between Python and PySpark is here. And when I work, I usually prefer to go to Python and then start out by there. And sometimes I hit some limitations. In Fabric, the PySpark notebooks are good and very fast, but sometimes there are you have to tweak something sometimes. And then when you switch to PySpark, for example, because it has a different compute, you can put it that way. You have to manually install things yourself, which I have in the PySpark notebooks. What I'm trying to say, in the Python notebooks. What I'm trying to say is that even if they are both notebooks, they're completely different computes. And Python have some pre-installed things, pandas, polars, arrow, and so forth. And PySpark might not have these, but then they have some other things installed. And I think I used an hour or two to find the right Delta Lake version for Python. I'm going to be back for that. But you need to use 0.18.2, which is actually a quite old version. So, but yeah, let's get started. The first script I have here, that's just a copy script. And I'm using, I also think I'm having here, I'm using, in this example, I'm using the Hive partitioning for ingestion. And I know that it might be old. It's actually quite a strong tool. And especially if you're doing unstructured processing, Hive partitioning is super strong over Delta tables. I said it. Delta tables might not be the best choice in any case, but I can do another session about that. What we get from a Hive partition is that we are using the folders as the partition keys. And when we read the data set, the folders is actually going to be in the data set. So what I usually say is that when we're using Hive partition, we can utilize the partitioning as an annotation for our data. And I'm using that a lot when I'm doing unstructured data processing. Getting back to our example, so I'm reading a file. No, I'm not reading file. I have a source. I have a CSV called customers, and I would like to add it to my files, customers partitioned data set. And I can do a very quick Spark display so we can see how does the table look right now. And we can see we have 3 entries, and the CSV file contains 3 entries. If I do a copy, just copying in the file, it took like 1 second. And we can see that we have added it to our table. And that's the fastest way we can ingest. It's just to copy in the file. So there's no need to read up the files into a Spark and then write it down again, or read it into pandas and write it down again. Copying files into the data set is actually always the fastest if your setup allows that. Then when we have the Hive partitioning, we can, and this is arrow, but it could also be pandas. We can actually utilize it. So this is the same data set we used to read Spark, and they're more or less the same in performance, so that there was not so much there. But then you might be like, okay, Henrik, I'm not so much into Python. Can I just use SQL? And actually, you can do that. What we are seeing here is something called an unmanaged table. And what we do is that we're actually creating a table, but we are telling, okay, the data for the table is outside. It is in the file section. And when we have, we don't even have any tables, so I'm going to create it in a minute. Oh, we have it. I can remove it and then create it. Yes. The thing about Fabric is that this Data Explorer window, the table section is something called Manage Data. So every time I write to the table section, I'm also writing some information about the table into a metadata store called the catalog. It's not documented, but there's a catalog in every workspace we have, and it's holding all the metadata about our warehouses, our lakehouses, and so forth. So what I'm going to do with this is that I'm creating the table, which I just deleted, and I'm telling the table, okay, the data is actually located on the files, and this is due to the partitions. Every time we are loading a table like this, and we have partitions, we have to run this command after every ingestion. It took 8 seconds, and then I can start to use a SQL instead of Python. Then the question might be, what about if we just use Delta tables? Because we like Delta tables. And then we are moving a bit away from copying in files. But then again, we can create a Delta table actually very fast. And I'm kickstarting. Oh, sorry. Apparently my session has run out. I forgot this one. So what I'm doing here is that I'm creating a table, and I can also delete it here. And for good measure, sorry, I didn't forgot to show you that the X table I created before was actually there. So yes. So again, I'm writing from the source, but instead of copying, I'm just writing up the CSV files and saving them as Delta. I'm using pure Python, and it took like 3 seconds to do it. And that if I'm going to do it like this, we can see it was copied over. As I said before, the fastest way is to copy, but also we can actually just use Python if our data set is not that big. It only took 3 seconds. I can try to do the same with Spark, and as you probably saw, it took some seconds to do, if I'm allowed. Sorry about that. So what I'm doing here is that the process of reading from a source, writing to Delta with Python, and then with Spark. And Spark was about twice the what's called the performance. Python was half the performance of Spark. So I'm kickstarting a little bit about the Delta RS, and let me continue that. The Delta RS is a library. It's a Delta Lake library for Python. It's actually for Rust, but it can be used for Python. And it's not fully on par with the one Spark has. It's when we have Delta Lake, we have different integration, and we can have, for example, Delta Lake for Spark, we can have Delta Lake for Flink, and we can have Delta Lake for Python, and so forth. And they might not be the same in features, but almost close to. And the Python Delta Lake is quite fast. It doesn't have all the overhead as Spark has with going out to the clusters and the executioners are going to write. It can just take the memory and write down. This downside is that we sometimes have to write a little bit more. We can see we have more Python here, and you're going to get the notebooks because there's a lot of code. But compared to Spark, Spark is almost no code. And I think we also sometimes see it in SQL. Sometimes this large SQL scripts is perhaps performing faster than the small. So there's ups and downs with everything. But let's go a few steps further. Because where Python also shines is actually when we are going to ingest data from APIs. I've read a lot of articles about how to do it in Spark, and there are many of them which is actually getting it a little bit wrong. So let me explain. If we have a REST API and we're using Spark, so we have a big cluster, then some of the articles are saying, okay, just make a user-defined function and then call the REST API. And I have made an example what there can be of issues by doing this. So this is my example. And I have created a web service which can return a JSON with three objects. And then I've created an endpoint in Asia. And what we're seeing here is that live metrics, which is showing the API we're going to ingest data from. And if I run this one, I have a table with 100 rows, and I'm going to call the API with the what's called user-defined function, as which many articles are writing that this is the way to do it. And what we're seeing is that the API is really getting hammered. It is getting called with 100 calls, and many companies or enterprise APIs actually have a throttle where they're saying, okay, only so much calls can be done per second, and we might also exhaust a database which is behind the API. And you can also see what we're seeing here is that the Asia function is actually scaling out because there was so much load at a short time. So it's really not the way to do it unless you would like to take down your production database or something like that. So the reason for that is that when we're using an Asia-defined function, the function is applied to every row in the table set. And I did it with 100. Imagine if I had a table set of 1 million. That's 1 million call in a very fast time to one poor API. So, and you can also see that this result of that is actually the same data redundant for each row we had. Then the question could be, okay, instead of doing it for every row, what about if we just do it for every execution that we have, or partitions of data that's not necessarily the same? So I've made an example where I just have 5 partitions and calling the same REST API, because that must save some resources when calling. And what we're seeing is that I'm still getting a very redundant data. And the reason for that is when we scale out and call at the same time, we must pull down the same data. So using this approach, using a lot of resources, but it also gives some more work to clean it up, to do a distinct on this data set, to make it look like what we actually pulls out of the API. Then we can do another approach. Let's say we are using the driver node. That's a common thing where we're saying, okay, the driver node can run some Python. So let's use the driver node to access the REST API. And then we use an executioner to store the data. It's a better way, and it has been the way to do it for a long time before we got the Delta RS, Delta Lake library. And I'm not going to run it because it's going to take some time from us, but you can say it takes around 1.5 minutes. And that's a long time for pulling down, in my book, pulling down 3 JSON objects from a REST API. Then we have the last one. So if you're having a Python notebook, we have a server. The least we can get is 2 CPUs. We do a little extract script called the REST API and use the same CPU to save to branch. Let me show you that again. And the code is looking like this. And as we can see, it's much like the Spark edition. It only took 3 seconds. And we can also show it. So I think in my book, at least, 3 seconds is more preferable than 1.5 minutes. And again, we're using Spark just to show the 3 lines of code. It'll get there at some point. There you go, 1/2 minute. So yeah, so it was a little bit in the ingestion space where we can get some benefits of using Python over Spark. And I also like to say that I've seen people do a lot of impressive things with Spark, but in the end, Spark is actually just a data processor. And we should use it as a data processor. I know we can bend it, like I showed in the beginning, where we can have API calls and user-defined functions, but it's not really meant for that. And there's also some other issues. What if API call hangs, then the cluster is just running, and we might not get any notification about it. So it can also open up for a lot of errors, which is quite hard to debug if we're using Spark for things it's really not meant for. But yeah, it is doable, but the Python edition for me is actually the fastest and the cheapest. And in comparison, I'm using it for some ingestion from the BC API, Microsoft Business Central, and we are running the lowest Python notebook instance with 2 CPUs, and it performs very well. So yeah, that's a good way to go. So speaking about performance and number of CPUs and so forth, when we are using a Python notebook and we only using 2 CPUs, then we're using half the compute as compared to one Spark node. The minimum Spark node we can get is 4 CPUs, and that's the extra small size. And yeah, I don't know so many who are not using the starter pool. I think most of us, when we develop, we just prefer the starter pool. That's 8 CPUs we are running there, at least, depending also how much we're scaling out. So we are using a lot less CU when we just go with the Python for the jobs, which is best fit for the Python. My good friend Just Blindberg have written about the notebooks and the CU consumption. It's a topic in itself, and I could probably also use a speak on that. It just says, in short, the fewer CPUs you have and the faster things run, the more cheap it is compared to slow and the number of CPUs. So it's a good read, and I recommend that.
Christian, we do have a question in the chat. So the question that somebody is asking is, hey, what if we just use a regular pandas data frame for our transformations, and then in the last cell we convert it into a Spark data frame, then write it to a lakehouse using Spark?
Yes.
at least then we have the in-memory processing of pandas, and then only use Spark to write to the lakehouse.
Yes.
So isn't the overhead then minimized?
No, sorry to say it. Let me go back just to the overview. So I also have written an article about that also, where I've done some performance testing. And we are leaping a bit forward, but no, let's take the question here. So it's true, we are doing the in-memory processing with pandas, and it performs well. The issue is when we are then doing a create data frame, then we are activating the driver and then a worker node, which is going to write down that data frame to the Delta Lake. If that takes longer, again, if it's a small data set, it might take 1.5 minutes compared to a few seconds. So the Delta RS is really the step forward. The only time where we shouldn't use Delta RS when we're using pandas and DocDB and what they're called is when we are going to have some features which might not be supported with the Delta IS. When you have a Delta Lake, you have the mean writer version and the mean reader version, and each version is covering a feature set. And yeah, they might not be supported, but if we're writing with Delta IS, everybody can read it. It might not be the case with Spark, actually. So if you're using column mapping, Delta IS will not work. So, but it works with most of the features. I hope it was a good question. It was a good question because it's a pattern which a lot of people do. So I hope it was a good answer. Yes, one of the issues with Spark has long been the small file problem. And I've done an example with JSON files, and this comes from a GDPR project I've been looking into, and also how can we do GDPR on raw files. And the thing is, one thing is to ingest data in and do some masking and so forth. But what if a customer says, okay, you have my data, I would like to be forgotten now? Then we usually have to do a post task on that data. So I've done some testing and have my test set of 15,500 small JSON files, and it's not fun for Spark. So it also depends how you do it, but this is where I just try to read the files. An important part here is that I did it without schemas, and we're going to look at that in a moment. And I just have to stop it after 20 minutes because it took too long. And the reason for that is when we don't give schemas, then the Spark just scans all folders of the files, and it has to figure out what is the schema, and it scans every files and opens every files. And we can reduce that by saying, okay, only scan 1% or 0.1% of the data set. But that's not a good solution because we know data grows, and then we're just postponing the problem. So, and there's also the issue that, okay, let's say if we have schema, then Spark has to create a so-called partition. Worst case, it does do it for each file, but it can also stuff more data into one partition. And then the last problem is when you have so many files, you get a lot of Spark tasks, and these tasks has to run on the cluster. And depending on how many executioners we have, and executioners are the one who do the job processing our data. Depending on how many of these we have, the execution times is going to be longer or shorter. For example, if you get 10,000 tasks and we only have one executioners, it's going to take a long time compared to if we have 1,000 executioners, then we can do 1,000 tasks at a time. So that was what I just explained more or less. let's look at some small files. So if we just read a lot of small file, I have a data set here. It's much like the one we have. It's just stored here, customer data set. I'm using the Hive partitioning. Again, here's just an example. I have a lot of files. I'm not going to run this because this is the one who takes probably a few hours. So I've made the same. I've just created my schema, and then I have the same expression with the schema. And then we can see, okay, it takes 1.5 minutes. So huge improvement, definitely. Then I have used this arrow we are going to speak about. So this is only using perhaps one CPU, and I can start while I speak. It's using one CPU, but what it does is it's threading out into 8 workers. So on one CPU, I have 8 threads, and each threads are traversing the data set. And then each, sorry about that. That's the downside by running Python in Apache Spark notebooks, is that we have to install the Delta Lake, but Delta IS. But that's the hit we can live with. So you're ready. Again, threading out each worker is reading up each file up and then combining it all to one big table. And we can see after 10 seconds, we have found all the files we are going to read from. And it usually takes around half to a full minute. And one CPU, and it's still a bit faster than Spark is. And again, it's the issue here is that it's a small file problem for Spark, and it's not Spark's strong point. Spark loves files around 1 gigabyte or 128 megabytes in that span. So when we're coming with a lot of small file, it's really struggling a lot, and we can see it actually only took 44 seconds. And what happens here is that we are reading the files and we are writing it to Delta tables. And yeah, they do the same job. Again, I know it's more code. Again, more code is not necessarily slower. In this case, it's actually faster. Again, in Fabric, Python can be a little bit quirky. That's why I've copied in an error I got a few months back. And I know Python went GA a few months back, but there has been some quirks. So sometimes it works, and then from one day to another, then it stops working. It's not a common issue. I think if you work with Fabric, then you have tried things like that over the years. So, but the thing is, I can also start this when I'm running. Back to the use case where, okay, I have a data set, I have a customer who would like to go in and delete their data. When we have unstructured data, unmanaged data, JSON files and text files and so forth, we have to go in and find which file we have to work with. So I have extended the code we have before with the 8 nodes. And when when a worker read up a file, it just scans the file and say, okay, is this ID? I have 2 IDs it's searching for. Is that in the file? If it's not in the file, it just discards it. And if it's in the file, it combines them to a data set. And again, that's why I have to switch it to Python. I remember. Let me try again. Yeah, so this is a pure Python. So yeah, what is it's finding values in a lot of small files where we don't have any indexing, and it usually takes also around half to a full minute. And that's also where Spark is not. Spark is good at structured data, things where they are in tables and so forth. The unstructured part can be what it does when it reads a JSON file is converted to a structured data set. So it's a bit challenged here. And we can see, I search some IDs. I can see what files they are in, and then perhaps I can use Spark for processing files and remove data here. Or I will probably just use my Python as well. So when we have a lot of small files, especially if they're JSON or any other text files, we can actually benefit also from looking in the direction of Python. So I've mentioned Arrow a few times, and I've mentioned Delta IS. So let's look at the Arrow and see what is it. So Apache Arrow, I think it's version 22 right now. And it has, over the years, I've been doing data for a lot of years, and it has actually become my favorite data framework. And you're probably already using it because it's very well hidden in all the libraries we are using. So Pandas is building on Arrow. It started to be built on Arrow on version 2.0. Apache Spark is using Arrow. When we are using a user-defined function, we have our tasks running on the executioners. Then if we have a Python user-defined functions, it spin up a new process and exchange data between the process and the executioners with Arrow. All these and more are using Arrow in some sort of way. Either they are building on Arrow, or they're compatible with Arrow. And yeah, what Arrow do is that, let's say we have a JSON file and we have a computer with memory. Then, of course, we have to read in the JSON file, and that could be Pandas. It could also be Polars. It could actually also be Spark. Spark has, for Spark 0.40, it now has a 2-arrow table. So we have our data set, and Arrow is like Parquet, so it compresses the data. It's actually quite similar to Parquet. It's not Parquet. If we have to pull it to some extent, we can say it's a Parquet for in memory, for data in memory. So we are reading in the data. It gets into the Arrow format. It gets compressed, and we would like to use, for example, DocDB to query this Arrow. What DocDB does is it's pointing to this memory space in the computer memory. So it has direct access. So there will be no conversion from, for example, Pandas to DocDB. When they exchange format, they only move the in-memory pointer. So it's actually quite snappy. It's also called zeroing copying because they're pointing at the same data set. Then if we do a transformation, then we get a new Arrow data set. That's what it is. But let's say we would like to store this. And now we're getting back to the question we had before. Why not use the create data frame? The reason is that if we're using Delta IS, our Delta Lake library, then it can also use Arrow. It can utilize the memory. So it's using zero copy. It just write it to the one-leg tables. And that's why it's also so fast, because there's no data movement. Of course, there's a movement when we go from memory to the one-leg, but there's no movement between the libraries we are using. And let me show you that. So I've made an example, and I've pre-cooked something. So I've made a test data set, and it takes raw in Python memory, a little above 11 gigabyte of memory. And I converted to a Pandas data frame. This is not important. It's just so I can write it to Parquet. So I have a large data set written to Parquet. So we can see I can just read it because we're going to use it. So in this case, it can be anything, but I'm using arrow raw to read the data. And it takes around 20 seconds, yes, 16 seconds. And we see in memory, the 11 gigabyte is actually compressed to 2.5 gigabyte. So when I created the data, I was actually forced to give it 4 cores to give it enough memory to create the data set. But now when the data set is ready and can read it in, I can actually utilize 2 cores as the normal minimum Python. If we look down here, we can see we have 2 V cores and we're only using 26% of our memory. 25 million rows, that's it's not a lot, but it's still significant if you ask me. So we have our arrow data frame, and we would like to have a pandas data frame. So we can do, we can just two pandas directly on the frame. And it took 1 second. So in this instant, and now I'm using a quote, we didn't copy it, but, and we didn't move data, but it became available as a pandas data frame in less than a second, and we can do a head on it. Let's say, okay, we have our pandas data frame. We got it here. Let's move that to a polars data frame. It takes a little bit longer. But again, now we have 25 million rows available in the polars data frame, and again, you can see the result in advance. So it's the same data set. Okay, DocDB. Many of us heard about DocDB, and DocDB, when it runs, it can scan a Python scope for arrow data frames. So I'm just saying pl.df. I don't even have to do anything, and then it can create create a data frame for that, and we can create right away. And if you see, again, 25 million rows, and we're just moving it around. And let's save it to a delta table. Just have to, I forgot to put override on it. So let's delete this one. So we don't have any tables. So let's write to completely new tables, which is actually a bit more expensive. And we do that in 3 seconds. So we have the table. It was this aggregation we wrote down. But as we saw before, pulling 3 JSON objects from an API and save that to a Delta Lake through Spark took like 1.5 minutes if we go some examples back. So to answer the question, we had first, if you can live with the features which comes with the Delta IS, and you're using pandas, always use the Delta IS library instead of Spark create data frame. You will save so much time and compute by doing that. But I've taken the arrow, you have to see arrow as the generic data frame, as the data frame we can pass around, and then we can decide on what Python framework we would like to process the data with. We can also do it in pure arrow, but many people prefer DocDB, or many people prefer polars or pandas, and etc. But if we are having a framework at an accelerator for Fabric and using Python, then arrow can be the generic data frame to pass around. And then, as I said, then we can decide later what the framework to process it with. So, and that reminds me of Microsoft came with this T-SQL artifact. That's a way to access SQL endpoints in Fabric. It only works in Python notebooks. As you can see, it's very easy and we can point at a DB, and we can bind it to a data frame, and we can do a select, and it's very beautiful. My only grief is, why didn't you use Arrow for this? Why do I know a lot of people are using pandas as it is returning, but it has just been so much cooler if it was an Arrow data frame, and then we could apply pandas on that, or polars, or so forth. But then again, it's not hard to go from a pandas data frame to an Arrow frame to polars or DocDB, and it's 0 copies, so it's okay, but it's just been a little bit cooler if you ask me. So this is actually one of my good friends, Matthew. He has written this book. He's one of the developers of Arrow. He's part of the Apache PMC. So he's probably the number one source in the whole world when it comes to Arrow. But as I said, it's the unsung hero. It's actually in almost any data tool we're using, at least which comes from Apache. So the thing about Python is also the thing with JavaScript from a few years back. It's like that there's always a new library. So that there's always a library of the week or day or the hour. It goes very fast. What I'm looking at, okay, there's some jobs to be done. And one of the jobs, it could be Hive partitioning support. It can also be Delta Lake support and data frames and SQL. And Fabric, the Python notebooks, comes with these at hand. They are pre-installed. I know I had to use the Delta IS, but that's also because my examples had some Python code in it. Python notebooks doesn't support the run command, so if you're using that, you have to switch to PySpark or let the Spark notebooks. But else, the other frameworks are out of the box. One minor caveat about that is it's also very old versions. So I'm very excited to see when Microsoft come with runtime 2.0. Oh, that was the can. If they have released some newer versions of these. What I'm looking into myself is that I'm looking for this Apache Data Fusion, and it's actually not included. It's very fast to install, but it's actually from the people who made Apache Arrow. At some point, they were like, okay, perhaps we should do an optimizer and a query engine, and they started on that, and then they separated from the Arrow project because Apache Arrow is only about in-memory data format. So, but from that, Apache Data Fusion came, and it's lazy loaded data frames. It supports SQL, and it actually don't own dataset, which DocDB might do. You just point at the data, you come with your recipe, and then it processes the data. It works with that. Instead of Spark, which is running on clusters, Apache Data Fusion can distribute its works out on the CPU. Polars can do that as well. So yeah, you might get scale-out processing within the same server, and then we are saving the overhead of the scale network. Sorry. So, but how can we use it? So there's the concept of the metadata-driven lakehouse. I have, together with Just and also Per to some extent, been out and speaking about Aquashack and how we can build a lakehouse, which is metadata-driven. And the concept is that we have the bronze, silver, gold, and then we have some engine which runs on data. So you specify some data, move data from bronze to silver, and usually this metadata is coming from the outside. And then we have some typical SQL, and I can see I'm a little bit over time, but I'm soon done. What I've done is that I've built something called AquaQuery, and I have two open source projects. I have the AquaQuery and I have the Aquashack, and they actually identical, but AquaQuery is based on Arrow and the Aquashack is based on Spark. And we have, due to some historical reason with my work, the bronze is called landing, and the silver is called base, and the gold is called curated. So we have a top notebook, which is the library, which has some functions which can be used in the Aqua landing to base. And then we also have base to curated. I did some testing. When I'm moving data from bronze to silver, aka landing to base, with Apache Arrow, it took 4 seconds. The same data took 55 seconds on Spark. When going for base to curated, on Arrow took 38 seconds, while on Spark it took 1.5 minutes ungefähr. Also, I have to be fair to Spark here, because there's the concept of single node Spark, where you have it all on one server, where the driver and the executioners are sharing the same server. And it was a bit faster, and I've created a table here. So Aquashack cluster Spark, and AquaQuery, which is Aquashack, and then the single node. So I think there's a significant performance between these. So the question is, of course, should we move away from Apache Spark? And the answer is actually no. Let me go back to this picture. As I mentioned in the beginning, that a lot of the things we are ingesting is actually small, and also typical if done right, and we have incremental loading. Moving from bronze to silver is actually also smaller batches. So when you have very specific workloads, Python can be the best option. Often the silver layer is built up to be large. We are moving a lot of batches, and then suddenly our silver layer is large. And we also often do more general querying. We can ask of anything of our silver layer, also of the gold layer. And when you have so large data set, it can perhaps be a Tera or something like that. Spark is actually is a better choice in that case. So this actually leads to the end. You can look them up. They're very easy to install if you just have 1 minute. We go in, and this is Aquashack, but the AquaQuery is the same. This setup file is a notebook. And all you have to do is either copy or import this notebook and run it. Then we'll set up the full lakehouse solution. So it's just an installer notebook. You don't have to do anything else. Yeah, it was actually all I have. I can also demo that if people have time, but it's up to you. So are there any questions?
We currently have no questions.
So yeah, perhaps it also was a lot.
Just a comment in chat, just a quick tip input. Based on a few conversations with Henrik, I have been looking into sharing Arrow tables or Arrow datasets between Python and Spark computes.
Is that a comment or a question?
It feels like a comment. Yeah, quick tip and input. So
it's just a comment or a tip.
Yes. Yeah, I can show you this quick if you.
Sure, we have time left, so.
Okay.
That's perfect.
Yes. So there's different way to do this. This is my fast way to do this. So I take a workspace, I create a new workspace. This was Aquashack AquaQuery, which is my Arrow-based. It's the same. I'm just using a trial. you know, the fabric trial periods, it reminds me of the WinRAR trial period. It's like never ending, but that's a good thing. Okay, just call it notebook 1. Yes, now we get a session, we will have a lake house within 1 minute. So that's how to either go with the examples I have with either Arrow or Spark. We can see things are starting to cook. So yeah, we should be able to see things building in. Yeah, so it was just a quick how to get started. I can go around just show a few things, but usually what I've learned is that people are going to look at it itself because there will be a lot of code to switch around. So yeah, that's all I have.